Hello and welcome to today's lesson on chi-square goodness of fit testing. Our objective is by the end of this lesson we'll be able to understand how to conduct a chi-square goodness of fit test and why they are important overall skill-wise. Okay, to answer the question of why we use chi-square goodness of fit testing. In our last unit, proportional testing, the most proportions that we could use in any test was 2. So if we want to do testing of multiple proportions, 3 or more, 2 proportion testing fails. We can't use our proportion intervals. We have to go to what's called a chi-square testing procedure. So our question for today, does the makers of Skittles claim that every color is equally represented? Okay, we're going to try to prove them right or wrong based on our statistics. Like all of our other situations, the first question we have to answer is, can we trust our answer? Chi-square testing is a little bit easier, less assumptions to test, because all we're looking at is the counts of categorical data. Now, the counts could easily become proportions, but in this case, we're looking at whole number values. So our assumptions, simple random sample, okay, is that reasonable to assume? And then the last piece that we need is our expected counts, and we'll see how we get those values, have to be at least 5 in each category. So all you need to do to verify these conditions is show your expected counts, and we build that within our table calculation-wise. The chi-square distribution is not a normal distribution. Okay, we can see the different degrees of freedom here. Okay, we can see that it's a skewed right graph, and as our degrees of freedom increase, we are going to get a distribution that becomes more and more normal overall. Okay, also notice one other fact of this distribution. It starts at an x value of 0. There is no such thing as a negative chi-squared value. Okay, our hypothesis statements are statements. They're not numbers. Okay, it's all about the proportional nature of what we're looking at. So the proportion of each color in Skittles is equal. The alternative is the exact same statement, and we just put the negation not into that alternative. So now, when it comes to our calculations, we have our chi-square formula. It's on your formula sheet that AP gives you. And the very first thing we have to do is we have to build our table. Okay, so this is Jack's data from yesterday when we were doing the Skittle experiment. And what we're looking at here is in his counts, 15, 19, 10, 12, 18. Okay, so those were all of the observed counts of his Skittles in the experiment. So now, how do we get our expected values? Okay, for our expected values, we add this all up to get a total of 74, divide by our 5 categories, and that's how we get our expected values. And in this case, they're all equal. Okay, dependent upon the problem could give you percentages, and then all you would do is take the percentage and multiply it by your total. We could do the same thing here. Okay, everything is 20% of the overall distribution, so we would multiply by 0.2 to get that value. So now, to do our chi-squared calculation, okay, you can either use the tables on the calculator or you can crank this out by hand, but when we're doing chi-squared, okay, we have to remember it's the sum of every one of these calculations. So we're working through 15 minus 14.8 squared divided by 14.8. Okay, the square and the denominator are important. The squaring makes every value positive because otherwise the values below average and the values above average would cancel each other out. And the denominator, dividing by the expected value, normalizes this calculation. So it doesn't matter if your sample is 74 or your sample is 84. Okay, the proportional part is taken care of by that denominator value. And then we would keep moving. 19 minus 14.8 squared over 14.8. Okay, and we would do that for the rest of our values to get our chi-squared value of 3.97. Okay, now chi-squares are not going to look like normal distribution or t-values. Okay, they are going to be larger values. So 3.97 might not be an alarming chi-square value. Okay, chi-square, like the t-distribution, needs degrees of freedom as a part of it. So in this case, the degrees of freedom is the number of categories minus 1. So in our situation, we had 5 colors, 5 categories, minus 1, which gives us a degrees of freedom of 4. Now, to find our p-value, okay, what's the probability of our chi-squared value? And it's always a greater than situation, 3.97. Okay, we can go right to the calculator and let the calculator do that with our chi-squared CDF. So second vars to get into our distributions. Chi-square CDF is down at 8. Our value that we get for chi-square is always a lower boundary. Okay, upper boundary, positive infinity, or 10 to the 10. And then we need our degrees of freedom, which we found already is 4. Okay, so we enter that in, paste that through, and we get a probability value of 0.41. Okay, remember what this probability value means. It means if Skittles are equally distributed, we will get observations like this 41% of the time. Okay, so that's not a rare outcome overall when it comes to these procedures. Okay, so now finishing up, we need a conclusion. Okay, so you can see this test works like any of our other tests. The same things we need each piece. So we need to state our evidence, our conclusion about the null, and a statement about the alternative in context. Okay, so based on our evidence, always compare your p-value to a significance level. In this case, we're going to fail to reject because this is a fairly common occurrence to get the Skittles in this proportion. Okay, and then the statement about the alternative. This evidence does not support the alternative hypothesis, which states that the color of Skittles, not Skittle, are not equally distributed. Okay, and that is our chi-square distribution. Okay, if you want some extra practice besides your Schoology assessment, okay, in-class packet problems 1 through 5 are all chi-square goodness of fit tests. Thank you and have a good day.